All right, welcome to AA 6-6, complex roots and imaginary numbers. And that is pretty much exactly what it sounds like. On my calendar, I have linked another video that kind of explains imaginary numbers a bit more. So you may want to check that out. So if I look at this particular polynomial, based on what we've done before, this would have a basic equation of y minus 1, 2, 3, 4. So y plus 4, not y, I'm sorry, x plus 4 times x plus 1 times x minus 2. If I multiply that out and I look at the difference in the direction changes, that has a minimum degree of 3, and that one has 3 real roots. Now something like this, because of the shape, we can guess that it would have a degree of 3 as well because of those shifts, but we also know from the equation, if we multiply this out, this would have 3 degrees. But it only has 1 real root. Sorry. And if we look at this x squared plus 1, we're going to deal with this down here in just a moment, because remember, when we're finding our roots algebraically, we're looking at what makes those zeros, and that brings in a complication. So where those other 2 roots actually exist and how we can write this in factored form becomes more complicated. So if I look at these 3 different equations, think back to your x minus h squared plus k form of your parabola. If this is x squared minus 25, that is a k of negative 25, which means our parabola is down with a vertex of 0, negative 25. If I have x minus 5 quantity squared, then that is going to be shifted 5 to the right. If we think about that in terms of what we know about our polynomials, that makes that 0. That's what our factored form is, and 5 makes that a 0. So that's a double root at x equals 5. On this one, x squared plus 1, that is a regular parabola shifted up 1. So I'm going to have that looking something like this, and that has no real roots, so that's 0, 1. So solving and finding those roots algebraically is relatively simple on the first 2. Add 25 to both sides. We could also factor that using the difference of squares and use the zero product property. So x plus 5 and x minus 5. So x squared equals 25. Square root both sides. And we have x equals plus or minus 5. The reason that's plus or minus is because negative 5 times negative 5 gives us 25, as well as 5 times 5. So then our roots here are 5, 0, and negative 5, 0. On this one, this is already in factored form, so we can just set x equal to 5. Or I should explain that further. Set that x minus 5 equal to 0. Another way to look at this is if we square rooted both sides, that would leave us with x minus 5 equals 0. Add 5 to both sides, so x equals 5. So we have a root at 5, 0, which we obviously saw above. Now on the last one, x squared plus 1, if we subtract 1 from both sides, we've got negative 1 equals x squared. If we try to square root both sides, we end up, I'll show you the calculator part for this, square root of negative 1, giving us a non-real answer. So that non-real answer, as it happens, so I'm going to write this as plus or minus the square root of negative 1 for our roots. That non-real answer is right here, and we are going to use that as I. That becomes our imaginary number I. And that can help us define those complex and imaginary roots. Just kind of further explained in that video that I'm going to link as well. So if I solve this, so this is up here for my x-intercepts, I make that a 0, and then I'm going to solve it the same way. Sorry, you can't see that. the same way that I did here. So what I'm left with is x equals plus or minus the square root of negative 1. Instead of writing the square root of negative 1, I'm going to write I. That's plus or minus. So x equals plus or minus I. And leave it at that. This one, if I subtract 4 from both sides, make that a 0 because I'm finding an x-intercept. Find that. So negative 4 equals x squared. Square root both sides. So now I have the square root of negative 4. Another way that can be rewritten is to take the square root of 4 times the square root of negative 1. And this is helpful to us because the square root of negative 1 can be written as I, and the square root of 4 can be written as 2. So this can be 2I equals x. And that would be a plus or minus as well. So that is imaginary numbers in a nutshell. There's a couple things that I want to go over. So I'm going to show you a few examples from the 6-6 worksheet. And then I'm going to tell you you should pause before I go on to the back side of the worksheet because you need to try to do those on your own. It's not going to be very helpful if I walk you through the entire worksheet. But let's do a couple. So there are some times when we're dealing with I that we are going to deal with it as though it's a variable. It's not a variable because its value does not vary. I's value is square root of negative 1. But there are times when we can't do much more with it than treat it like it's a variable. Like if I have 2I plus 4I, that's when I'm going to treat it like it's a variable because 2I plus 4I is simply 6I. And that is the most that I can do with it. Same kind of idea with 5 times 3i. 5 times 3 is 15. I is just still hanging out there, so that'd be 15i. However, when I get to e, got 2i times 5i. So that's going to give me 10i squared because I have the 2 times 5 for the 10. I times I gives me I squared. So if I equals the square root of negative 1, if I have the square root of negative 1 times the square root of negative 1, that equals the square root of negative 1 squared. So square and the square root, those undo each other, so that equals negative 1. And there are some difficulties with that I'm not going to get into because one of the things that we just accept is that I is the square root of negative 1 and I squared is negative 1. So if I have 10 times I squared, that's the same thing as 10 times negative 1, which is negative 10. Now, I'm going to have you pause if you have not done J, K, or L. I'm going to give you a second to pause. And then I'm going to move on and go through those with you because this is kind of an important concept. If I have I times I times I, these two i's, so I times I is I squared, which we now know is negative 1. So if I multiply that by I again, I'm going to get negative I. Now, let's say I take that again, I times I times I times I, chunk this off into sets of 2, I times I is negative 1. This I times I is also negative 1. Negative 1 times negative 1 is a positive 1. So it's not until you start multiplying I by itself, squaring it, cubing it, so on and so forth, that it becomes more number-like. So then if I take that again, I times I times I times I times I, two of those pairs are going to give me negative 1 times negative 1 times I. Negative 1 times negative 1 is positive 1, so this is just 1i, or just I. So the odd exponents are going to, switch between being I and negative I and I. For the odd exponents, the evens are going to switch back and forth between being negative 1 and positive 1. So on a couple of these, you need to pay close attention to how this is happening. So we've got this, these are just being added. So you're just going to drop the parentheses away and combine your like terms. Part B, you have to pay attention to that negative. It's going to change those into negatives. So I'm going to go ahead and do part D. Again, if you haven't done it yet, pause it and try it yourself. So if I'm multiplying this out, this is 5 times negative 3i and 5 times positive 3i. 5 times 5 is 25. 5 times negative 3i is negative 15i. 5 times 3i is 15i. And negative 3i times negative 3i is going to be negative 9 because of the negative 3 times negative 3, and then I squared. That's not simplified because we know that I squared is equal to negative 1. So we have negative 9 times negative 1, which gives us a positive 9. Now, what happens to the rest of this? Negative 15i and positive 15i add out to 0. So what we're left with here is 25 plus 9, which gives us 34. So if I'm looking at my patterns, and this shouldn't be terribly surprising with a difference of squares. If I've got an a plus some, like a plus b and a minus b, that's a squared minus b squared. If I have a plus bi times a minus bi, sorry, I think I said that all wrong. A plus bi times a minus bi, my middle terms, so what I mean by middle terms, I mean like these two, are going to add out to 0. So what I have is a times a, so a squared, and then bi times bi, so minus bi squared. So what happens there is I have a squared minus b squared times I squared. We know I squared is negative 1. I'm going to bring that up here. So a squared minus b squared times negative 1, which makes it a squared plus b squared. And that's my general for that complex conjugate. Something that we couldn't ever factor before now. So let's turn you over to the back side. And I'm going to just kind of briefly talk about these. I'm not going to go over every single one. So what we know from our polynomials and hopefully from back in Algebra 1-2 is if I have x-intercepts at negative 5 and 7, that means one of my equations can be x plus 5 and x minus 7. And I'm going to multiply that whole thing out. My factored form is going to be that x plus 5 times x minus 7. And the same thing is going to work here. This factor associated with the square root of 5, 0 for my root is going to be x minus the square root of 5, and this one's going to be x plus square root of 5. As I get down here to to 3i and negative 3i, those factors are going to be x plus 3i and x minus 3i. So I am going to go ahead and multiply that out with you. If I have x times x, that is x squared. X times 3i, that is 3ix. X times negative 3i is negative negative 3ix. And then here, negative 3i times 3i is going to be negative 9i squared, which we did on the other side is the same as negative 9 times negative 1, which is a positive 9. Again, our middle terms add out to 0, so I'm left with x squared plus 9. That's not factored form, sorry, that would be your standard form. So, keep in mind, if my factor is 3i, if my root is 3i, that factor associated with that is x minus 3i. If my root is negative 3i, then that factor is x minus negative 3i. So when we have a root, it's x minus that root for our factor. And that's where this is why you need a 3 by 3 instead of a 2 by 2. If I have complex roots of 5 plus I and 5 minus I, that means my factored form is going to be x minus 5 plus I. That's one of my roots, and this is my factor, times x minus, because it's always x minus your root. It's when you have a negative root that it becomes plus. And then parentheses 5 minus I. So that's where we have to be careful with our negatives. So the first one, I'm going to have the x. That negative is going to distribute here, so I'm going to have minus 5 and minus I. I'm going to do a little squiggly there. For this one, it's going to be x minus 5 and then plus I, because of negative being distributed to a negative. Oh, you can't see that over here, sorry. So, when I multiply this out, x times x gives me x squared minus 5x minus xi minus 5x plus 25 minus 5, plus 5i. And that's because these two are both negative. Down here, plus xi minus 5i, and then minus I squared. So, a few things add out to 0. My plus 5i and negative 5i, my plus xi and my minus xi, and this negative I squared, keep in mind that I squared is negative 1, becomes a negative 1, which becomes just 1. So, when I write this in standard form, I have, which you can't see, I'll scoot over, x squared minus 10x, and then over here, 25 plus our 1, so plus 26. So things like that you have to be pretty careful with, that you're differentiating between the root and the factor, and you make sure your factor is always x minus the root. So that takes you through some of the trickier stuff on the back side of that worksheet. Hopefully you did not just wait for me to walk you through all that and you tried it on your own. Make sure you complete that worksheet, because the more practice you get, the better it's going to stick. Alrighty, have a lovely day.